Hey guys, so this is section 6.12, expressing internal energy in terms of measurable quantities. In your textbook it says expressing internal energy, enthalpy, and heat capacities in terms of measurable quantities, but you already know how to do enthalpy and heat capacity. We've seen those in terms of things like the isothermal compressibility, the isobaric volumetric thermal expansion coefficient, so you know those. So let's just focus on internal energy. Starting with du equals TdS minus PdV, which is true for solids, liquids, and gases, as long as there's no non-expansion work done, no phase transition or chemical reaction. So starting with that, we're going to let temperature be constant and divide through by dV. That gives us on the left partial U partial V constant T equals, and then on the right T partial S partial V constant T minus P, because the dV's cancel there. But we already showed back in section 6.2 that this term right here, partial S partial V constant T, is equal to partial P partial T constant V, and we also showed that's equal to alpha over kappa T, or we saw that it is. So just replacing partial S partial V constant T with partial P partial T constant V, and then alpha over kappa T, the isobaric volumetric thermal expansion coefficient and the isothermal thermal compressibility, we get this expression right here. Partial U partial V constant T is equal to alpha times temperature minus kappa sub T pressure over kappa T. This term, by the way, the partial U partial V constant T, is called the internal pressure. If you do a unit analysis on it, you'll see that it has units of pressure. It's called the internal pressure. So now we can write the total differential of the internal energy du, which is just partial U partial T constant V dt plus partial U partial V constant T dV, as this. This term right here we saw already was just the heat capacity at constant volume dt, and we just showed this term right here is equal to alpha T minus kappa T over kappa T. So there we have it. du is equal to this expression right here. Everything on the right, guys, things we can look up in tables or measure. Heat capacity, constant volume, alpha, kappa, measure the temperature, pressure, dt and dV, and we've got it. So let's do a little example. Given the isobaric volumetric thermal compressibility and the isothermal expansion and the isothermal compressibility for ethanol at 298, these numbers right here, we want to calculate the internal pressure at 332 Kelvin and 1.14 bar. And of course, we're assuming that alpha and kappa T don't change from 298 to 332, and that's probably a good assumption. And then next, if the that's supposed to be, no, that's right. If an external pressure that's equal to that internal pressure, which is this right here, is applied to 3.14 cubic meters of ethanol, how much would its volume change? So let's do that. First of all, finding the internal pressure, partial U partial V constant T, this expression we just derived, plugging in the numbers we got, alpha, temperature is 332, kappa T, pressure, and kappa T. Again, please check my math, but I got like 3.44 times 10 to the third bar, 3,440 bar. And now to do the second part, to see how much volume it changes, okay, we can use the isothermal compressibility, right, kappa T, because that's defined as the change in volume with respect to pressure at constant temperature, and divided by 1 over the volume. So what we do is we just basically multiply 3 by volume, and then dP, right? So take these bottom terms, bring them over here, integrate from initial pressure to final pressure. And the right hand side we just have integral of dV from one volume to the other. We're going to assume, and it's a pretty good assumption, the volume and the isothermal compressibility do not change over this pressure range. So we don't have to worry about their functional dependence. We can just pull them out front of the integral. So we get volume kappa T times delta P is equal to delta V. So we just plug in the numbers and we get that the delta V, the change, is about 1.19 cubic meters, which is, almost half, right? Actually, yeah, really close to half of what it started out. What did it start out as? 3.14. So that's more than half. All right, so there we go.